Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand humans? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. All right, well, let's get well away with our questions. And I know that you've had some questions coming in, haven't you, Chris, to thenakedscientist.com?
Yes. If anyone wants to send questions in, chris@thenakedscientist.com. I've heard from Tim Ream, who says, Dear Naked Scientist, I recently brought a new chronograph watch, in other words, timepiece, and I noticed that the glow-in-the-dark paint glowed much brighter and longer with less light input. So how do these newer generations of glow-in-the-dark materials, like you see on watches, for example, actually work? Fascinating question. The answer is it's a chemical trick, and they use various chemicals. The first one of these glow-in-the-dark chemicals was actually made in the early 1900s. It was about 1905. And scientists discovered that if you took the chemical zinc sulfide, so zinc with some sulfur atoms linked to them, and you added a little bit of copper, so in the mixture there was the odd copper atom, when you shone light at this substance, it could store the light energy, and then later the light energy could be released again as a very visible green light. And by adding the copper, this is called doping, and it made it happen better and more efficiently. And so they would use this chemical to make things like watch hands glow. But the problem is that they quite quickly run out of the energy they've stored from being illuminated. So then people thought, well, how do we get the energy into the chemical to make it glow? So they started mixing it with radioactive things. So the first glow-in-the-dark watches and clock faces were used using radium. And radium is an intensely radioactive chemical, and when it radioactively decays, it spits out radioactive energy, and this is soaked up by the zinc sulfide, or at least it was in the old days, and that then excites the zinc sulfide, giving it the energy it needs to glow, and that's why these radium paints were very effective, because radium is so energetic, it breaks down so quickly, and has a very long half-life as well, so it tends to last for a really long time. Your glow-in-the-dark effect goes on forever and ever and ever. But of course radium is quite bad. It's intensely radioactive, and the people who used to paint radium onto clock faces often used to lick the tips of the brushes, and this led to radium poisoning, and they would develop nasty cancers of the head and neck because of the exposure to the radiation chronically in the course of their job. So these days we use safer alternatives, thankfully, and scientists have recently sort of tweaked the mixture a bit in the last 20-30 years and found that if you take strontium, which is another metal, and you make a compound called strontium aluminate, this is really, really good. It works the same way, so you put energy in from visible light, and what this does is to put some of the electrons in the substance into a higher energy state, so the electrons soak up the energy, and then they fall back to their original starting position, releasing the energy they stored in the process, and that's the glow. Now, you can do this with visible light to give it the energy, or you can again use a radioactive substance. And up until I think fairly recently, Rolex, for example, they may still do this, used not radium but tritium, a radioactive isotope of hydrogen, to do the same trick. So you have some tritium painted on with the glow-in-the-dark paint, and the radioactivity passes the energy into the paint, which then spits it out as visible light, keeping your watch visible all the time. And I think many military instruments still use that technique today.
Absolutely, and it's always good if you hold them up to the light, then they glow a little bit more. And we've got Pat on the phone. Good evening, Pat.
Hello.
Hello. What's your question for Dr. Chris?
These scientists are making the H bombs and testing them bigger and bigger and bigger. Is there any fear when they might throw the Earth off its axis?
I think that's unlikely, because the Earth weighs 6 with 24 zeros kilograms after it. So the Earth is very, very heavy, and as a result, you would need an absolutely enormous degree of impact or energy being released in order to make the Earth move at all. I think the energy unleashed in the Boxing Day tsunami 5 years ago, the energy in that may have made the Earth wobble very, very slightly, but it was almost imperceptible in the grand scheme of things. And that it doesn't even, that would eclipse the energy unleashed in an atomic weapon many times over, the energy released there. Yeah. So I think we're probably okay from an Earth perspective. It's much more likely that in the course of making these weapons, we'll blow ourselves away in the process. So I think the planet will be okay, we probably won't.
All right, Pat.
Right, thank you very much.
Thank you very much. Bye-bye.
Cheerio.
So what we have now is a question from Keith, Dr. Chris. He says, am I being silly, but can you explain how a glowworm works?
No, not being silly at all, because it took scientists a little while to suss this one out. When we say glowworm, there is a range of things that can be meant. There are the kinds of glowworms you will find in the UK, and then there are other kinds of glowworms that you will find in other countries. And one of the most famous conglomerations of glowworms, and if you ever get the chance to go and see this, I would recommend a trip to Waitomo in North Island, New Zealand, which is the most amazing place on earth. I think it's amongst one of the modern wonders of the world, actually. I was there about 5 years ago, and I actually interviewed one of the people who works there and went on a little tour. And it's the most amazing place. It's called the Glowworm Cave. In fact, these glowworms are little grubs. They are worm-like that live on the roof of the cave, and they have in their tail a dense blue light. It's the most gorgeous sight because there are so many of them in this cave that you can actually read a book by the light they're producing. It is incredible. The way they do this is they have in their tail a number of chemicals called luciferins, and they also have an enzyme called luciferase, which breaks down the luciferins, and to do that it also needs energy, which comes in the form of a molecule called ATP, adenosine triphosphate, and oxygen, which it gets from the air. And when it mixes that lot together, the product of that reaction is light. And it's a beautiful, gorgeous, light blue light. It's actually a cold light because the enzyme doesn't produce heat, it turns all the energy into light. So it doesn't boil the bug by it turning its light on, but it can control the light, it can turn it on and off at will. And it uses it for two reasons. For a number of years, these glowworms grow by dangling from the roof of the cave these very thin threads of silk, which the glowworm dribbles blobs of stickiness onto. And if you look at them closely, they call them fishing lines. They're these things, maybe a foot long, each of these strands, decorated with little blobs of a gluey substance. And the glowworm lives up above where all these fishing lines are dangling down above the water. And it turns its light on, and things like flies and gnats and other insects that are buzzing around above the water see the light, and they fly up towards it, and as they're attracted to the light, they stumble into these fishing lines and get stuck. And the glowworm can feel the line tensing and flexing with the thing stuck on it, so it winds it in, winches it up, and it then eats whatever it finds, and that's how it gets its food. The glowworm then grows, and when it reaches a critical size, it pupates, and it emerges as a gnat. And this gnat doesn't have a mouth, so it has to fly around, find a mate with it, lay eggs, and then die, all within the space of just a few weeks. And it uses its light under those circumstances then to find that mate. So it uses it for two reasons, and it's all down to a clever chemical reaction. The ones that you will find in this country are a bit different, but they still use the same enzymic machinery and the same chemical reaction to produce their light.
That is absolutely fascinating. Thank you so much. All right, let's go to our phones now. We've got Tony there. Hello, Tony.
Good evening, madame.
What's your question for Chris?
Well, it's a strange one, really. It's really, what is a headache? It's as simple as that.
Well, headache can mean lots of different things to different people, Tony.
Yes, I'm sure.
The commonest cause of a headache is what we call a tension headache, and as the name suggests, it's because of stress. And this occurs because the muscles which form your scalp and insert into the scalp over your head, and which get tense when you are tense, those muscles have a bit of a spasm, and it's uncomfortable, and you experience this pain, which is a bit like a vice or a gripping pain, usually around the front of the head. Now, those types of headaches usually resolve spontaneously, or if you just take yourself away from whatever is making you stressed, or have a drink, calm down, they normally go away. If they don't, then a simple dose of paracetamol, a simple painkiller, can usually make them go away. But there are other reasons why people get headaches that can be a bit more sinister. You can also get something called cluster headaches, and this is often in young men. We don't know exactly why they happen, but you get these very severe headaches. They come in clusters, and they can appear, cause a problem for a while, and then disappear, very poorly understood. Then there are migraine headaches, which are not related to the muscles on the head, but actually to the blood vessels, we think, inside the brain. It seems in migraine that bits of the brain develop an abnormal pattern of electrical activity, and this causes the blood vessels supplying that bit of the brain initially to constrict. And this vasoconstriction, the clamping down of blood vessels, does two things. One, it is the prelude to developing the headache, but it also produces visual changes. You will see on the affected side of the body, in other words, the brain is crossed over, so the right side of your brain affects the left side of your body. So on the affected visual world, so the left side of your visual world, what you're seeing on the left side, if the right side of your brain is affected, will develop funny wiggly lines and patterns. And that's called the aura prodrome. And that lasts for a variable length of time, but it warns you there's a very bad headache coming. And then the blood vessels open up in the brain and dilate and throb. And this is the headache. And it can last a number of hours. It can be associated with very intense sensations of nausea. It can also make people feel very photophobic. They're scared of the light, and light makes the headache much worse. So people tend to go into a dark room where it's quiet. So that's migraines. Other reasons why people get headaches can be things like the pressure inside the skull becoming too high. This can happen for various reasons when people have tumours, for example, or if the blood vessels draining the blood from the brain get blocked, pressure can rise inside the head, and that will also produce a headache. Then there are other things like what they call space-occupying lesions. If you have a brain tumour, sometimes this can take up space inside the head, put the pressure up, and put tension on the meninges, the linings around the brain, and that hurts. And then there's actually things like a stroke. Now, if you have the cessation or obstruction of blood flow into the brain doesn't actually, despite being made of nerve cells, it doesn't actually have any sensation itself. So a stroke, despite the fact that you're killing lots of brain cells, is painless. But if a blood vessel pops inside the head and you bleed into the space around the brain, this is excruciatingly painful. And people describe it often as a thunderclap headache. All of a sudden you have this pain that starts and comes out of nowhere and is excruciating. And that's called a subarachnoid hemorrhage. And that can be often a hallmark of that is this very excruciating headache. And then, of course, there are things like trauma. So if someone drops something on your head and bashes it, you then get injury to the bone or bruising over the bone and the lining over the bone, the periosteum, and that's sore in itself. So I think that's a sort of relatively comprehensive roundup of the reasons why your head might hurt.
Incidentally, which one of those is a hangover?
Well, a hangover is a bit of a combination of dehydration, because I probably should have mentioned that if you don't drink enough water or enough liquid during the day, that can also produce sensations of a headache. And that's probably because everything shrinks a bit and your brain might shrink a little bit, and this might apply tension to blood vessels and the lining, the meninges around the brain, and irritate them. And another reason why people get headaches, of course, talking about the meninges, is meningitis. If you have infection of the layers around the brain, which can be viruses or bacteria, then that also will produce quite a severe headache. And if people get a severe headache and this photophobia, scared of the light, then that's a worrying sign, and they should go and get checked out. But a hangover probably is a bit of dehydration and chemical irritation to the meninges, and as a result you just feel goddamn awful. Then you take a couple of paracetamol, rehydrate yourself, and you feel better.
Tony, thank you.
Very much indeed.
Thank you, Tony. Now, Chris, let's have one of your questions, because I know people have sent them into the Naked Scientist. What's your next question, Chris, that you can answer?
I've got an email here from Katrin, who's 10, and she says, if hot air rises, why is it colder at the top of a mountain? In other words, if you're in your house at home, hot air rises above the cold air in the house, but why is it then if you go up in an aeroplane or you climb up to the top of a mountain, it's getting colder and not warmer? Well, many people think, well, if you're going up in the air, you're getting closer to the sun, so shouldn't it be getting warmer anyway? The reality is that relative to the distance that it is to the sun, it's about 100 million miles or so, the few thousand feet that you go up in the air is trivial and therefore negligible. So there's something else going on. And the reason is that sunlight, which falls on the Earth's surface, brings energy to the Earth at the rate of about 1 kilowatt, 1 bar electric fire, for every metre squared of the planet's surface. That heat and light is soaked up by the ground and then re-radiated, given off again, as long-wavelength infrared heat. And it warms up the ground and the air and the environment close to the ground. But by the time you've gone up a long way from the ground, or you're at the top of a mountain, there's not much ground around to radiate heat into you to feel warm. So automatically it feels colder. That's the first point. The second point is that up in the air, up in a mountain, or at the top of a mountain, is very exposed. So there's enormous amounts of wind chill factor. Also, on mountains, for instance, there's a lot of snow. So the ground doesn't really soak up a lot of energy. The white snow reflects the energy straight back out into space. So the ground itself is cold, and therefore the environment locally remains cold. But the most crucial point is the one about the rising of warm air. Because when you warm up air, which happens close to the ground because the ground is warm, the warm air is less dense, so it rises. Now, as the air rises, of course, the pressure of the atmosphere drops the higher you go. That's why, when you get to the top of Everest, for example, water will boil at about 80 degrees compared with 100 degrees that it does at sea level. That's why it takes much longer to boil an egg on the top of Everest. And as the air rises and expands, because the pressure is lower, when you expand a gas, the temperature drops. It's a bit similar to if you take a gaseous aerosol, your deodorant, for example, and spray it in your armpit. It feels cold, because basically what you've done is to expand the gas that was under pressure inside the aerosol into your armpit. And because the gas expands, it gets colder. And that lowers the temperature at altitude, which is why when you take off in your aeroplane, the temperature outside, when you're at cruising altitude, is about minus 70 degrees C. So very chilly indeed.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. There's an email that's come in from Mary in Felixstowe. Dear Dr. Chris, I've always been curious about moons on fingernails. Do they serve a purpose? And also, what is the cause of thick toenails? Could it be poor circulation? Chris?
Well, when you look at a nail is just an aggregation of the protein keratin. Keratin is the same stuff that hair is made of. And in a fingernail, it's merely hair that's grown in a slightly different way to make a fingernail. And it grows from something called the nail plate. And in the nail plate, there's a special collection of stem cells there, which are making the keratin and then squashing it together and forming the nail. And when you see those little moon shapes, that's actually part of the nail plate, where the nail unites with the nail bed, the surface of tissue where the nail grows out from. Nails are dead, effectively, just like hair is. Now, the reason that you can get crumbly nails, and this happens more commonly when you get older, unfortunately, is because of our microbial friends. This is going to gross people out, but actually those thick, yellow, discoloured, crumbly nails that get very thick and can stink a bit, they're actually down to fungi. Usually fungi and moulds and yeasts. And the common culprits, there's one called Trichophyton, and this is very common, that gets into nails. There's also yeast like Candida albicans that causes athlete's foot and things like that. And then you've got another one. It's called, I had to write this one down because I couldn't actually remember it. It's Scopulariopsis. Is the name of the mould, less common, and there's another one called Fusarium. So there's all these different moulds and yeasts which live in the environment. They live in damp, warm places, so they love your shower. And when you go for a shower, your feet get wet in the shower. It picks up a few of these moulds and spores and things from them, and they get onto the nails. And if you don't dry your feet off properly and dislodge these things, or if they get into underneath the nail, then they can begin to grow. And they invade the nail, and the whole nail becomes a network of tiny bits and fibrils of these moulds that are growing into your nail. And it's the process of invading your nail in this way that makes them crumbly. And the treatment is to use either ointment or you can take a tablet. And either way, it's an antifungal medication. You have to be quite dedicated with the ointment. You have to paint it on for up to 6 months, and then eventually the nails get better. The tablets, there's one called terbinafine, which is quite good, but it means you have to have a blood test to make sure that it's not messing up your liver after you've been taking it for a little while. But very, very common, picked up by grotty showers. So bleach your showers, but don't bleach your feet, and try and dry them off properly after you've had a shower or a bath, and then hopefully you won't catch them.
Let's go to the phones now. We have Dave on the line. Hello, Dave.
Hello.
You're through to Dr. Chris.
Now, humidity. If you've got a higher humidity in a room, will it improve the efficiency of the central heating?
Okay. Well, humidity means how much water there is in the air.
Yeah.
And the higher the humidity, the more water there is in the air. And people tend to talk about percentage humidity because there's a certain amount of water that air at any temperature can hold, and the more saturated the air is, the higher the relative humidity. The thing about water in the air is that although the temperature can be higher, if you've got water in the air, that can also soak up energy, and it means that it needs more energy to make the air hotter because it's damper. So if you wanted to spend the least on heating, if you have lots of water in the air, that's a bad idea because you've got to heat the water up as well as the air.
Yeah, but
whereas if you have a drier room, then it won't be such a problem.
Yeah, but once it's heated, it stays warm.
That's an argument, which is that once you've got it hot, the air, because it's got water in it, is going to hold on to its heat for longer because you've got energy locked up in the water, and that's absolutely true. And that's why people say when it's hot in summer in Britain, and it's because it's so humid, it feels much hotter than it really is because it's much harder for you to lose heat. And what's going on there is that when you want to lose heat, you do a number of things. One of them is you put lots of blood through your skin, which radiates away heat, but you also sweat. And when you sweat, you're evaporating water from your skin, and the evaporation takes with it latent heat of evaporation. And that's why it feels hotter in a humid environment. I'm not sure what contribution to your overall heating bill excess humidity will make, though. I'd need to look into that. It's an interesting question. I'd need to have a look.
I thought a certain amount of humidity would actually improve it rather than dry air. There's nothing to stop the infrared from just going straight to your wall.
That's true, because the infrared the atmosphere, air, is relatively transparent to infrared, whereas if you've got some water floating around, it might soak it up. But the point about radiant heating, with infrared coming out of radiators and things, is that it hits the objects in the room and makes them warm, and then they radiate out some energy at you, and you feel warm. So I think it swings and roundabouts, actually, because if all the air gets too hot, then it will go up into the roof and take your heat with it, and the objects that it didn't warm up won't be as hot, if you see what I mean.
Yeah.
Hot stuff then, Dave. Bye-bye.
Thank you, Dave.
Now, John in Stowmarket says he has a set of underwater lights for his pond. Would they be OK to use out of water for garden decoration?
Well, it depends on the lights and what their rating is, because some electrical appliances designed to run in water are rated higher than they would be rated if they are exposed to air, because water's a very good cooling medium. So you have to check that the bulbs or whatever the mechanism that they make their light is, whatever that rating is, it can not overheat when it's run out of water. Pumps are very sensitive to this, and I know he's talking about lights, but pumps, for example, the electric motors in them, if they were in air, would have a fan driving the airflow over the pump inner rotor, which would keep it cold. But underwater you can't do that, so you have to rely on the pump body conducting a lot of heat away from the windings and radiating it out or passing it into the water via that route. And if you take the pump out of the water and run it above water, it gets really, really hot really, really quickly. So you have to just make sure with any aquatic appliance, when running it outside of the water, that it's not going to overheat.
Mike in Colchester says, is it true that when you break a bone, when it heals, the bone is actually stronger in the place it was broken?
It probably is true to a certain extent. What happens when you break a bone is that, obviously, in adults, not in children, but in adults, bones are much stiffer and they snap, and you can end up with the two snapped ends separating from each other a bit. Sometimes not totally, sometimes they do separate and get displaced by quite a bit. But between the two cut ends, there will be bleeding locally, because bone is very vascular. In the middle of bone, there is bone marrow, which has a very rich blood supply, and that's where there are lots of stem cells that make all your blood cells. And then around the bone, is a structure called periosteum, which is a fibrous protein layer, which has got blood vessels in it, which nourishes the actual bone itself. So if you damage a bone, all those structures bleed, and you will produce a blood clot between the two broken ends and locally in the tissue. And this blood clot will very quickly after the injury, as long as the limb is immobilised and fixed in place, it will be invaded by cells called osteoblasts, which come out of the cut ends of the bone, or the broken ends of the bone. They invade the blood clot, and they begin to do a number of things. They begin to lay down protein, which forms a meshwork between the two broken ends of the bone, and they also begin to hang on that meshwork new bone salts, so new calcium phosphate starts to form there. And initially when they do that, they lay down just a mess. Lots and lots of bone structure gets laid down, and it's big and bulky, it's disorganised, and it's not very strong. But after this initial repair has happened, new cells come in called osteoclasts, and they begin to break down the bone, and then osteoblasts at the same time make it up again. And this does a process called remodelling. And so the bone gets built up and broken down, built up and broken down, and you get the whole thing repaired, but very often it'll be a little bit bigger than where it was broken, where it was before it was broken. So actually probably it ends up a bit stronger, because the bone matrix, though, could be denser.
Oh, I'll tell my mum about that. Dom in Newmarket has given us a call. He says, my grandma used to have a microwave. Where it was positioned in the room, there was a phone antenna very close. Anyway, the microwave used to switch itself on and off, and Dom wants to know why it was and if it had anything to do with the antennae. Chris?
Well, it could be. When you have a radio signal, this is an electromagnetic wave. It's a bit similar to a microwave. Mobile phones use microwaves to communicate with their base station. A bit different in frequency from the one in your kitchen, but similar. But the point is, when you have a source which is making a source of electromagnetic radiation, such as an antenna, an aerial, a phone ringing, something like that, it can generate radio waves. And they can be a bit dirty sometimes. You can get a whole range of different frequencies coming off. And if you have another object which is electrical and contains metal, then those radio waves can induce a current to flow in that other object, and that could be the reason why the microwave was misbehaving when the phone rang, because it was triggering abnormal currents flowing in the microwave, and it was fooling the electronics in the microwave that would normally control the timer and things like that, and when the microwave went on and went off. So my best guess would be that that was the reason.
Now, we've just got time for one more question sent in to nakedscientist.com, so let's have one last one from you, Chris.
Well, this is very interesting. Keith wrote in and said, how is past climate recorded in things like tree rings and corals? Because we hear scientists talking about using tree ring data or coral clock data to read what the climate did in the past. And this is very interesting because you might say, well, tree rings, that sounds a bit too simplistic. But in fact, it's a really sensitive measure because trees live for a really long time. And every season that the tree grows, it lays down a new ring of tissue in its trunk. So if you take a cross-section of a tree, and some trees can live 1,000 years, you can see 1,000 years worth of temperature data, because trees grow more when the weather's nice, when it's warm and when there's rain, than when the weather's bad. So if you look at the relative thickness of the tree rings, you can immediately see something about what the growing conditions were like, spanning a very long period of time. The next thing you can do is to then actually chemically analyse the tree rings. And this is what scientists have been doing in more recent years, because if you go into the tree ring and extract some of the chemicals, one of the things you can look for is an isotope, an alternative form of oxygen. And oxygen comes in three flavours, three isotopes. There's oxygen-16, which is the most common. Then there's a rarer one, oxygen-17, and a slightly different one called oxygen-18. And because the oxygen-18 is much heavier than oxygen-16, you get what's called fractionation. So when the sun beats down on the sea and evaporates some water, water which contains oxygen-16, being lighter, is much more likely to get evaporated than the heavier stuff with the oxygen-18 in it. So if you look at the relative proportions of this 16 and 18, which is in the tissue of the trunk of the tree, you can tell how much rain must have fallen in that particular year. So that's how you can use tree ring data. Corals are quite similar. Corals also grow, just like tree rings, so if you take cross-sections of old corals, which grow on top of each other, and they can record timescales going back many thousands of years, you can see the rings as the corals have grown, and again, they grow well in warm water, and in warm weather, when the conditions are ideal, they grow very little, make just very thin rings when conditions are poor, and you can also analyse in the calcium carbonate that the coral is made of, the oxygen isotopes, and again this gives you some clue as to the relative abundance of oxygen-16 and oxygen-18 in the water, and by comparing the ratio of those two things you can work out how warm it must have been, because the warmth would have been evaporating water off of the sea, leaving behind more of the heavier form of oxygen. So you can work out what the weather was doing, how warm it was, and how well things were flourishing, just on the basis of those simple measurements. So these are really important time capsules that climate studying scientists tend to rely on.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, Look us up online at nakedscientists.com.